Welcome back to our series on Linux forensics. Today, we're grabbing our digital map and compass because we're charting the most critical piece of evidence there is, the file system itself.
Okay, so picture this. A Linux server's been hit. You've got the disk image sitting in front of you. Now what? It can feel like searching for a needle in a digital haystack, right? Well, the answer is you need a map. You need to understand the system's digital blueprint.
All right, here's our game plan. First, we're going to define our crime scene. Then, we'll learn how to read the map of the file system. After that, we'll start following the evidence, from user activity to system configurations, and then we'll check the security logs. We'll wrap it all up with a case study to see it in action.
So, in any Linux investigation, the entire file system is your crime scene, the whole thing. And it all starts from one single point, a single character that holds the entire digital world together. And that character? It's just a /. That's it. That slash represents the root directory, and it is the absolute top of the food chain. Every single file, every single directory we're going to talk about lives somewhere inside of it.
Now, the cool thing is, this structure isn't just random chaos. Most Linux systems follow a set of rules called the File System Hierarchy Standard, or FHS. For us as investigators, the FHS is our treasure map. It tells us where things are supposed to be, which makes it way easier to spot when something is out of place.
Okay, so let's make our first stop on this map. In any investigation, one of the first things you want to know is, what were the users doing? And that includes both the good guys and the bad guys.
And that leads us straight to our first key location, the home directory. The best way to think about home is like a digital apartment building. Each user on the system gets their own apartment, which is just a subdirectory with their name on it.
So yeah, its official job is to store user files and settings. But for an investigator, home is an absolute goldmine. This is where we find the most direct evidence of human activity. The documents they were working on, the websites they visited, you name it.
So when we dive into a user's home folder, we have a checklist. We're looking at things like .bash history, which is literally a record of every command they typed into the terminal. We're digging into their browser folders to see their web history, and you better believe we're checking their downloads and .ssh folders because that's often where attackers grab stolen data or find keys to other systems.
Okay, so we've looked at the regular users. Now it's time to talk about the system's most powerful user, root. The root account is special, and it doesn't live in the home apartment building with everyone else. It has its own private residence.
And that residence is the /root directory. This is the home of the superuser. Any activity you find here, any command in its .bash history, was done with the highest possible privileges. This is where we look for the big stuff, evidence of major system changes or signs that an attacker successfully escalated their privileges, which means they went from a regular user to having the keys to the entire kingdom.
All right, so after checking on what the users were up to, our next job is to understand how the system itself is put together, and more importantly, has it been manipulated by an attacker? For that, our map leads us to the etc directory. Just think of etc as the system's central control panel, or its main fuse box. All the configuration files that tell the machine how to behave live right here.
Now, etc is supposed to hold static configuration files that don't change much, but attackers absolutely love this place. Why? Because if they can modify a file here, they can create a backdoor. Even better, they can achieve what we call persistence, which is a fancy way of saying they can make sure their malware runs automatically every single time the machine reboots.
So, as an investigator, the moment I get to etc, I'm on high alert. I'm asking, have any new user accounts been added to etc password? Are there any sketchy-looking scripts in the startup directories like etc init.d? What about in the cron directories, which schedule tasks? An attacker could easily plant a malicious job there to reinfect the machine over and over.
Okay, so we've seen the system's blueprint in /etc. That's how things are supposed to be. Now, let's go find the record of what actually happened. It's time to check the security tapes.
And those security tapes are stored in the var directory. The name stands for variable data, which basically means it's designed to hold files that are constantly changing and growing. And the most important of these, for us, are the log files.
You know, if etc is the plan, then var is the journal. It's where the system writes down everything it does all day, from who logged in to what errors it ran into. For building a timeline of an attack, this place is absolutely critical.
These logs are where we track the intruder's movements. The offlog file, for example, will show us every single login attempt, both the good and the bad. The syslog gives us a general play-by-play of system events. And we also have to check places like bartemp, which is a favorite hiding spot for malware because files there can sometimes survive a reboot.
And this right here, this comparison, is really the heart of the investigation. You take the system's blueprint from /etc and you lay it over the security camera footage from /var. Any place where those two don't match up, that's a red flag. That discrepancy is where you're going to find the intruder's footprints.
Finally, let's talk about a really special place called proc. Now, this isn't a normal directory with files stored on a hard drive. It's a virtual file system. Think of it like a live dashboard that gives you a real-time view right into the system's engine while it's running.
And on this dashboard, you've got all sorts of dials and readouts. You can see real-time memory usage, what the CPU is up to, and crucially, you can look up any running program by its process ID, or PID, and see exactly what executable file it came from and what network connections it has open. It's incredibly powerful for live analysis.
Okay, we've learned the layout of the map. Now, let's actually use it. Let's walk through a quick hypothetical case study and trace an intruder's path through the file system we just mapped out.
So, step 1, staging. The attacker gets in and drops their malicious tools in /tmp, a temporary folder that anyone can write to. Step 2, persistence. They need their malware to survive a reboot, so they hide a script in /etc/init.d. Step 3, execution. That script now runs and goes straight to a user's /home directory to steal SSH keys and command history. And finally, step 4, covering their tracks. They try to edit or delete the log files in /var/log to hide the fact that they were ever there. See how they hop between these key locations?
But here's the most important part. The evidence from any one of those directories only tells a fraction of the story. A truly solid forensic report is all about connecting the dots, linking that malicious script in Etsy with the stolen data in home and the tampered logs in var. That's how you build the complete narrative of the attack.
So, understanding the file system hierarchy is the absolute foundation of Linux forensics. It takes what seems like a chaotic mountain of data and turns it into a structured crime scene, telling you exactly where to start looking for clues. The map doesn't solve the case for you, but you have no chance of solving it without one.